Hello, everyone. Welcome back to CPE 517-WS Digital and Computer System Architecture. This is part 5 of lecture 6. We talk about paging and cache indexing. This is actually very, very interesting part. Okay. So, as you remember, assuming we have like, okay, sorry, let me get back. Okay, assuming we have this 0 to 31, total 32 bits. Okay, this 32 bits, assuming it's 4 KB, so it's 12 bits for page number, and then 20 bits for virtual page number, right? 12 bits for page offset and 20 for virtual page number. So, well, you should also understand that we have partitioned this 32 bits into cache tag, set index, and line offset. Right? And even we use virtual memory, but the mapping from the physical memory and the virtual, let's see, we'll put it this way. Virtual memory is not unique. I have virtual memory 0x55. You also can have the virtual memory of 0x55. So using virtual memory to decide which cache block should we put, this could have duplications and also could have conflict. So then it goes to, should we use the physical page for indexing and the physical page for tagging? This is the best, right? But clearly we have to translate the virtual page number into physical page number in order to do that. That can be time consuming. Not good. We can also do virtual indexing and physical tagging. This is not very good, right? So because we can use virtual indexing and then we're gonna suffer from potentially two different virtual addresses mapped to the same physical address, right? Like this virtual address and this virtual address go to the same physical address. Then we're gonna have duplications because we have different index, because the virtual index virtual address is different, and the virtual index could also be potentially different. The timing is better, right? Why? Because we can use the virtual index and the physical tagging when we're translating the index and go to the specific block, we can do the translation. So can overlap the fetching of the tag and the translation of the index, right? And the virtual index and the virtual tagging, the timing is the best, right? Because you can directly use virtual address to do both index and tagging. But the problem is you can both have the like a signaling problem, like the same physical address go to different virtual address, with the same different physical address go to the same virtual address. Okay, we're going to talk about both of them, and this is not physical index and virtual tagging is not used. Okay. First thing first, physical indexing, physical tagging, or physical index and physical tag. This is actually very straightforward. We'll basically do the translation, TLB translation. After we do translation, this has to be done before, right? After we do this translation, then we can do indexing and paging and tagging. It's slow, but it's simple. Right? For virtual index and physically tagged, it's good because you can parallelize the access of TLB and indexing the cache. Right? So it's good. But you could have a problem with signaling. First, it does not have a harmony, right? Because the same virtual address will definitely not map to different physical addresses. But the reason is also straightforward because you use physical tagging. So we always use, because we use physical tagging because different physical addresses will lead to different cache sets. They will not go to the same cache set, right? How about similarly, right? Different virtual addresses map to the same physical address. This is going to introduce duplication problem and consistency issue. Oh no, this is the correct one. So assuming we have this address and the index is here. Since we use virtual index, so we can directly use virtual memories for indexing, so we can directly go and fetch the correct cache set. Well, because these two virtual addresses map to the same page, then we actually cache the same page in two places, right? This leads to inconsistency issue. So how do we solve this problem? A simpler way is try to make this index small. Why? Because the page offset, this range of value is also physical bit. If you still remember, we do VPN, virtual page number, we translate it into PPN, right? And then this plus page offset. It together goes to physical address, right? So we know this page offset, this is actually physical. It's unique. So you will, if this is unique, then these two pages, these two processes, if they have same page offset, they exactly locate the same specific page, the same specific location, or at least the same specific page, then the index is gonna be the same. They're gonna go to the same location, right? There's no duplication anymore. So can you guys pause the video using 5 minutes to solve the problem? Like for a system with a 4K page, we need the maximum set count to be 128. What is the maximum cache block size? This is the equation we give to you. Maximum number of sets equals page size divided by cache block size. We didn't solve it. Okay, and then it should be 4 multiplied 10,000 divided by 128. It's 32. So the maximum, what's the maximum cache block size? It's 32. Well, clearly we cannot have always make it so small, right? Like our cache could be bigger. So in this case, we could also use a write through. Like whenever you write something to the cache, you drop it right to the memory. Or with flash cache, we have a context switch, means different processes go to the same physical page. And then when you have a context switch, just flash it. Okay, so then it goes to even more optimization about the time. It is virtually indexed and virtually tagged. So this is even faster because we can directly use physical virtual addresses for both accessing the cache and verify whether the cache is required. So, well, this is fast, definitely, but it has two problems. First is homony, second is synony. So homony, we're going to discuss later. Similarly is the same, like two virtual addresses go to the same physical address. And then homony is the same virtual address maps to different physical addresses. Why? Because imagine a case, you have this problem that we have a context switch. Previously, this virtual address maps to this specific physical page. And later, I have a context switch, this virtual page is swapped out, right? And then when you come back, we're gonna allocate a new physical page to this same virtual address. Then you're gonna have different copies of physical addresses mapped to the same virtual address. This is gonna introduce the homony problem, right? So how do we deal with this problem? I think we can either use process ID in the cache or flash cache upon the context switch. Okay, that's it for this one.